Hello, this is Dr. Hanaa Assil, and this is Unit 2 of May 2024 in the Pearson Edexcel International A-Level Chemistry. So let us take a look at the questions and discuss the answers. This was the first question, an enthalpy level diagram for a reaction with an intermediate is shown. Which arrow shows the enthalpy change for this reaction? Now, remember that the enthalpy change delta H is the difference in energy between reactants and products. So you should realize that the arrow labeled A is the delta H for this reaction. If we look at the other arrows, also please remember that that arrow B would be the activation. Sodium chloride dissolves in water to form a solution because of the interactions between sodium chloride and water. What are these interactions? So, sodium chloride, when it dissolves in water, you should know that sodium chloride is ionic. So, what kind of interactions between the sodium chloride ions and the water molecules? Is it dipole-dipole? Well, when do we have dipole-dipole? You should know that dipole-dipole interactions are between polar molecules, simple molecular structures that are polar due to differences in electronegativity between its atoms. So it has a slightly positive end and a slightly negative end. So there is dipole-dipole interaction between the molecules due to the attraction of the oppositely charged ends. This is not what we have when we dissolve sodium chloride in water. What about hydrogen bonds? Hydrogen bonds happen between compounds that have hydrogen bonded to an electronegative element. So alcohols, for example, when they dissolve in water because they can form hydrogen bonding with the water molecules. What about ion dipole? Yes, sodium chloride are ions. The ions will be surrounded by the positive or negative ends of water. You know that the hydrogen of water is slightly positive, the oxygen in the water is slightly negative. So the negative ions like chloride will be surrounded by the positive end of water, the hydrogens, and the sodium positive ions will be surrounded by the negative end of water, which is the oxygen. So this is the kind of interactions between sodium chloride and water. What about London forces? What are London forces? London forces are between simple molecular structures, simple molecules that do not have permanent dipole, but they will have induced, temporary induced dipoles due to the repulsion between the electron clouds of the molecules. So this causes again a slightly positive end and slightly negative end, and the attraction between these oppositely charged ends, this is what we call London dispersion forces or van der Waals forces. Equation represents the reaction for which the enthalpy change is the mean bond enthalpy of the CCl bond. So in the carbon tetrachloride, we want the bond enthalpy for one bond. So which of these equations represent the bond energy for breaking one CCl bond? If you look at these equations, it should be this one, because this one is breaking 4 CCl bonds, but we're going to say the moles divided by 4. So actually we're talking about just one CCl bond. This question is about boiling temperatures. Which isomer has the highest boiling temperatures? Well, what determines the boiling temperatures? You have to remember, boiling temperature is higher if we have more carbons, we have less branching, that means longer chains. Straight chains will have higher boiling temperatures than branched. And if we have hydrogen bonding, the more hydrogen bonding between the molecules, the higher the boiling temperature. So here, of course, we're not going to have hydrogen bonding. There is no hydrogen bonded to an electronegative element. So the only thing we have here, we're comparing between branched and straight chains. So if they all have the same number of carbons, then the one that is a straight chain is the one that has higher boiling temperature. All the others are branched, they will have lower boiling temperature. Which compound again has the highest boiling temperature? Again, what are we comparing between? Pentane. Pentane is something that has 5 carbons. Cyclopentane again has 5 carbons, but this is regarded as this is the cyclic form, so it is just like the branching. So it will have lower boiling point than the straight chain. So between pentane and cyclopentane, pentane would be higher. But then we are choosing also between butane 1-ol, and butane 1-ol is something that has a hydrogen bonded to an electronegative element, so the molecules would have intermolecular hydrogen bonds. And hydrogen bonds are strong and need more energy than the simple London forces between the simple molecules like pentane. So butane 1-ol would be more than pentane. What about butane 1,4-diol? Well, this has 2 OHs per molecule, and that means each molecule can make 2 hydrogen bonds with other molecules. So this is more hydrogen bonding, more energy needed to break these intermolecular forces. So this would have the highest boiling temperature. Steam is passed over heated magnesium. Which reaction occurs most readily? Well, we know that if we compare the reactivity of metals, some are very reactive and react with cold water. And when they react with cold water, they form the hydroxide plus hydrogen. But some metals like magnesium do not react with cold water quickly, so we react it with steam. And when a metal reacts with steam, it gives the oxide plus hydrogen. And of course, any metal less reactive than hydrogen would not react with water or steam or acid at all. So magnesium here is reacting with steam. So first of all, it should give the oxide, not the hydroxide. So B and D are totally wrong. We're choosing between A and C. What is the formula of magnesium oxide? You should realize that magnesium, valency 2, oxygen, valency 2. So magnesium oxide is MgO, not Mg2O. So B is wrong because this would happen in cold water and this is very slow. C is wrong because the formula of the magnesium oxide is wrong, and of course here the formula of magnesium hydroxide anyway is wrong. What are the products formed when lithium nitrate and calcium nitrate are heated separately? So we're heating lithium nitrate and calcium nitrate. I'm going to remind you that nitrates of group 1, like sodium nitrate or potassium nitrate, when they are heated, they form the nitrate. So that is sodium nitrate plus oxygen. But that is for group 1, not group 2. Now, Lithium is in group 1, but it acts as if it is in group 2 when we're talking about heating lithium nitrate. So lithium nitrate acts as if it is group 2. So both lithium nitrate and calcium nitrate, when they're heated, they give the oxide plus nitrogen dioxide gas, which we said is a reddish brown gas, plus oxygen. These are the products for both lithium nitrate and calcium nitrate. Group 2 compounds give different colors in a flame test. The best explanation is that the cations have different what? So if we're doing a flame test, why do the group 2 compounds give different colors? Remember, we said the color arises from what? The fact that when we heat the compound, electrons gain energy, jump to a higher energy level. So this is called an excited state. But the electrons don't like to stay like this. They like to come back. And when they come back to their original energy level, they emit the energy that they had absorbed. So this is what we see as different colors. Now, why do we have different colors? Because the gaps between the energy levels are different. So the amount of energy absorbed and then emitted by electrons of different compounds will have different amounts of energies, and therefore we see them in different colors. 2 tests were performed on an unknown ionic compound. Silver nitrate solution was added to an aqueous solution of the compound, forming a white precipitate. So they put silver nitrate with the compound, it gave white precipitate. Which type of compound gives white precipitate with silver nitrate? Remember, that means it is a chloride. Then they said the flame test gives a red flame. Now, which metal ions give a red flame? You should know it's either lithium or strontium. So my answer should be lithium chloride or strontium chloride. So that is the answer. Which compound needs exactly 9 moles of oxygen for complete combustion of 1 mole of the compound? Remember, complete combustion means reaction with oxygen to give carbon dioxide plus water. So basically, we're going to write out the equation, balance it, and we want to determine which of these will need 9 moles of oxygen. So that first one needs 8.5. The second one, if you balance it, it needs 8. The third one needs 9.5, and it is this last compound. If you write out the equation and balance it, you will find that we need 9 moles of oxygen. Which solution remains clear on addition to barium chloride? So we're reacting each of these with barium chloride. For example, in A, we are reacting barium chloride with sulfuric acid. So what should we get? Barium sulfate plus hydrochloric acid. Now, will this solution remain clear or will it form a precipitate? Well, which substances form precipitate? You should know this. Which substances are soluble? So they will not form precipitate. They will remain colorless solution. Any sodium, potassium, ammonium salt is soluble. All nitrates are soluble. All acids are soluble. So if we look at the products for A, barium sulfate is actually a white precipitate. Remember, this is the test for sulfate. We add barium chloride, it gives a white precipitate. So the solution would not remain clear. We will have a white precipitate. What about barium chloride with silver nitrate? Well, this will give silver chloride. Again, you should know that silver chloride is a white precipitate. because this is actually the test for chloride. If I add silver nitrate to anything that has chloride, it gives a white precipitate. What about sodium nitrate? Well, if I'm reacting sodium nitrate with barium chloride, what does it give? It gives sodium chloride, and we said all sodium salts are soluble. And it will give barium nitrate, and we know that all nitrates are soluble. So this is actually the one that will give a clear solution when we add barium chloride. With sodium sulfate, again, this is something that has sulfate, so it forms barium sulfate, which is a white precipitate. In a titration, a conical flask containing 10 centimeter cubed of 1 mole per decimeter cube sulfuric acid is neutralized by this amount and concentration of potassium hydroxide. The titration is carried out using methyl orange as an indicator. What would be the color change at the end point? You should remember what are the colors of methyl orange. If I put it in a base, it's yellow. At neutral or end point of titration, it is orange. In an acid, it is red. So we're starting with what? We're starting with the conical flask having acid. That means we're starting from red, and it will become neutral, so from red to orange. What is the concentration of potassium sulfate solution produced by this reaction? Well, what were we doing? We were reacting this amount of sulfuric acid with this amount of potassium hydroxide. So we should get the number of moles of acid. You know that number of moles is concentration times volume. Again, I'm reminding you, please do not put the volume in centimeter cubed. We have to divide by 1,000. So this gives 0.01 mole. So this is the number of moles of acid. What about the base? The number of moles of the potassium hydroxide was 0.8 times 25 over 1,000. That's 0.02 mole. Now we look at the relationship in the equation. If we have information about both reactants, we need to determine which one is excess and which one is limiting, because we're not going to use the one that's excess, we're going to use the one that is limiting. So according to the equation, the number of moles of potassium hydroxide should be twice the sulfuric acid, and that's exactly what we have. So the number of moles of either of them can be used to determine the potassium sulfate. So based on that, the number of moles of potassium sulfate is either the same as the acid or half the KOH. So that's 0.01. Now we are looking for concentration. Concentration is number of moles over the volume. What is the volume? Remember, we put 10 centimeter cubed of sulfuric acid on 25 centimeter cubed of potassium hydroxide. That means at the neutral point, the total volume is actually 35. So that's what you use to get the concentration, and that gives a concentration of 0.29. Information about uncertainties in each reading used to measure the volumes of the solutions in this titration is shown. So we are told that the uncertainty in using a pipette is this, and the uncertainty in using a burette is this, and we're asked which statement is true. Well, let's take a look. When we use, first of all, what have we done? We have used a certain amount of sulfuric acid. We put it using a pipette. We put the potassium hydroxide from the burette. So when we use a pipette, we fill it to the mark, and that's it. So we're making only one measurement using a pipette. So the uncertainty for that measurement is 0.04. But when we use a burette, remember, we need to determine initial reading and then final reading. So you actually read the burette twice. So if we're looking at uncertainty in using the pipette, it is 0.04 over the volume of the sulfuric acid that we put using a pipette. But when we're looking at the uncertainty in the use of a burette for potassium hydroxide, we read the burette twice, so the uncertainty is twice, 2 times 0.05 over the reading that we took times 100. So the total uncertainty here is 0.8%. So if we look at these choices, this is the correct choice. Again, remember, the pipette is read once, so you use the uncertainty once. The burette, you have initial and final. That means the uncertainty times 2 over the reading times 100. The boiling temperatures of halogens increase down group 7 because on descending the group, what happens? So if we're going down group 7, fluorine, chlorine, bromine, iodine, why is it that the boiling temperature of iodine is higher than bromine? Well, looking at all of these, you should realize that as we go down, the number of electrons in the molecule increase. Remember, these are simple molecular structures, so they have weak van der Waals forces between them or weak London dispersion forces between them. But as we go down, the molecule or the atom has more electrons, and that means stronger London dispersion forces. So remember, as we go down group 7, what is happening? First of all, the boiling temperature increases. Also, you should remember the electronegativity decreases, so we cannot say bond polarities increase, and reactivity decreases, and this has nothing to do with the boiling temperature, and the only thing related to the boiling temperatures is the number of electrons increase in the molecule as we go down, and that means stronger London dispersion forces that need more energy to be broken. Bromine and chlorine each have 2 stable isotopes, bromine 79, bromine 81, and we have chlorine 35 and chlorine 37. Which statement is true? Well, atomic radius of the 2 isotopes is different, greater or less than? Well, you should know that isotopes differ in what? They differ only in the number of neutrons. The isotopes will have the same number of protons, same atomic radius, so it doesn't make a difference, same electronegativity, okay? As we go down, this first ionization energy, if he says the first ionization energy of chlorine is greater than that of bromine, well, that is correct. But this is basically because we're comparing chlorine to bromine. We're not comparing the isotopes of bromine or the isotopes of chlorine. So both isotopes of chlorine will have the same first ionization energy, and both isotopes of bromine would have the same ionization energy. But comparing chlorine to bromine, you should realize that the electron in chlorine is nearer to the nucleus, more strongly attracted, so needs more energy to be removed. This question says cyclohexane with this density and aqueous iodine, density more than 1 gram per centimeter cubed, are shaken and left to stand. What colors are the 2 layers that form? So we have iodine aqueous, that means iodine dissolved in water, and we're going to mix it with cyclohexane. Again, remember that when iodine aqueous is mixed with cyclohexane, some of the iodine dissolves in the cyclohexane, and you should know that when iodine dissolves in organic solvents, it is purple. The aqueous iodine originally is yellow. Now, which one is the lower layer and which one is the upper layer? Remember that if we say that density of cyclohexane is less than 1, that means cyclohexane will float on the water. So that means the lower layer will be the yellow one and the upper layer is purple. Okay, then this question says 4 containers of the same dimensions hold samples of a gas. For container 1, the diagram of the Maxwell-Boltzmann distribution of molecular energy for this gas shows the activation energy, the mean molecular energy, and the most probable molecular energy. So this is the curve, and for container 2, we are told that the temperature is increased. So we have this curve, and then we're going to increase the temperature. For which values would the energy value change? Now, when we increase the temperature, what happens to the Maxwell-Boltzmann distribution curve? Remember, increasing the temperature means all molecules gain kinetic energy, so all the molecules will have higher energy than what they started with. But the total number of molecules is still the same. So if the molecules have higher energy, that means the curve shifts to the right, then, and the total number of molecules is still the same, then the peak has to go down. So which of these lines or which of these energies will change? Remember that activation energy does not change if you increase the temperature, but the other energies that he's talking about, which is the mean and the most probable and so on, these would change because the curve has shifted to the right. For container 3 at the same temperature as container 1, the pressure is lower. For which values would the number of particles at that value change? So, if we have this kind of distribution at a certain pressure, what happens if the pressure is lower? If the pressure is lower, then the particles spread out more. So if there is a certain volume we're talking about, the number of particles in that volume will all decrease. So the number of particles for each energy would decrease, and I would have the whole graph going down. So in that case, all the values would change because all the shape of the curve has gone down and the numbers at each energy is lower. For container 4, at the same temperature and pressure as container 1, the walls of the container act as a catalyst. So now we're putting a catalyst. What happens if we put a catalyst? Remember that the catalyst provides an alternative pathway with lower activation energy. So the activation energy in presence of a catalyst is now further to the left, and that will change the number of particles that have energy higher than activation energy. This question is about reactions of halogenoalkanes. When halogenoalkanes are heated with potassium hydroxide, the products depend on the conditions. Remember, we said halogenoalkanes with potassium hydroxide. Would that be in aqueous solution? Then we have something happening. Or in ethanol? Then we have something else happening. So the first question says, state what condition other than a suitable temperature and concentration of potassium hydroxide would give a high yield of alkene. So if I have a halogenoalkane, I'm reacting it with potassium hydroxide in presence of what in order to get an alkene? Remember, halogenoalkanes with potassium hydroxide in ethanol would give the alkene, and that type of reaction is called elimination reaction. Remember that in this case, the hydroxide ion is acting as a base. It takes up the proton from the neighboring carbon in the halogenoalkane, and the electrons go to the carbon-carbon to form a double bond, and the Br leaves with the electrons of its bond. So this is an elimination reaction. Then the next question says, state what condition other than suitable temperature and concentration of potassium hydroxide would give a yield of alcohol. When does a halogenoalkane produce an alcohol? We need to react it with potassium hydroxide in presence of water in an aqueous solution of potassium hydroxide. So if it is ethanol, it gives an alkene. If it is aqueous, it gives the alcohol. And in this case, the hydroxide ion is acting as a nucleophile that attacks the slightly positive carbon, and the electrons between the carbon and the bromine go to the slightly negative Br. So in this case, the OH is replacing the Br, so this is nucleophilic substitution. Complete the mechanism for the reaction of potassium hydroxide with the chlorobutane to form butanol. So we want the mechanism in which the hydroxide replaces the Cl. So you should know that the oxygen of the hydroxide has a lone pair of electrons that attack the slightly positive carbon, and the electrons between the carbon and the chlorine go to the slightly negative chlorine to give the alcohol by replacing the Cl by an OH. Give two reasons why, under the conditions used, the reaction between potassium hydroxide and 2-iodo-2-methyl-propane is faster than the reaction between potassium hydroxide and 1-chlorobutane. So we're comparing between the reaction with 2-iodo-2-methyl and 1-chlorobutane, and we're told to explain why the 2-iodo-2-methyl is faster. Well, one factor that determines whether the reaction is faster or not is it a CF bond, CCl bond, CBr, or CI? So as we go down group 7, you should realize that the carbon halogeno bond becomes weaker, more easily broken, and that is because the halogen becomes bigger, less attraction forces between the bonding electrons and the positive nucleus of the halogen. So the Ci bond is weaker and more easily broken than the CCl bond. Now, what other factor do we have? One of them is tertiary and the other is primary. And you should know that the tertiary halogenoalkanes are more reactive than the primary. So tertiary more reactive than secondary, and secondary is more reactive than primary. In a titration between a weak acid and a weak base, indicators do not give a distinct color change, so other techniques must be used. Our technique, or one technique, is thermometric titration. So here we're doing taking the temperature of 30 centimeter cubed of dilute ethanoic acid in a polystyrene cup. Ammonia solution of a certain concentration is added to the acid in the polystyrene cup in separate 5 centimeter cube portions. After each addition, the mixture is stirred and the temperature measured. A student carried out the experiment and plotted the points. Find the end point volume and maximum temperature by adding appropriate lines of best fit to the graph. Remember, if we have points like this, we should join the points going up and the point going down, and where they meet, that is the highest temperature and the end point volume. So from this graph, the end point volume is 21.5 and the maximum temperature is 27.6 degrees Celsius. Calculate the number of moles of ammonia added at the end point. Well, what did we say? At the end point, the volume was 21.5 from our graph. That's what we got. And we are told that the concentration is this, so I can get number of moles. Number of moles is concentration times volume. Again, remember, divide the volume by 1,000 first. So this is the number of moles of. The reaction that occurs is shown. Calculate the enthalpy change of neutralization for this reaction. Give your answer to appropriate number of significant figures, include a sign, and so on. So, first we need to get Q, the quantity of energy. Q is mc delta T. What is M? Well, he put 30 centimeter cubed of dilute ethanoic acid into the polystyrene cup, and then he kept adding until the end point volume of the ammonia was 21.5. That means M is the total volume. We know that we use volume as if it is mass in grams because we assume that the density of the solution is the same as density of water, which is 1. So what is the total volume? The total volume is the 30 of the acid plus the 21.5 of the ammonia. So the M is 51.5. What is delta T? Delta T is the difference in temperature. So the difference in temperature here is the 27.6 minus the initial temperature from that graph. So that is 6.9. Put that into Q. Q comes out to be 1485.4 joules. You remember that Q here comes out in joules. Then we need to use that to get the enthalpy change, the delta H. How do we get delta H? Delta H is Q over N. So what was the N? We calculated the N of ammonia is this. So the delta H is Q over that number of moles. That comes out to 53.05. What is the sign? This is in kilojoules. I divided the joules of the Q to get the Q in kilojoules, 1.485, and then divide by the number of moles. Now, why did we put the negative sign? Of course, that's because the temperature increased. When the temperature goes up, that means the reaction is exothermic, and that means the delta H must be a negative value. Okay, chlorine dioxide, ClO2, can be used to treat water to make it safe for drinking. The molecule is a free radical. One suggested structure is shown. Remember, when we have one electron on that atom, it is called a free radical. Now complete the dot and cross diagram for this structure. Use dots for oxygen electrons and crosses for chlorine electrons. So we know that oxygen originally has 6 electrons of its own, so it needs 2. So that oxygen on the left is having already, we're told they are double bonds, and you should know that a double bond means 2 electrons from the oxygen, 2 electrons from the chlorine. Now, the oxygen on the other end, we're going to use the 2 electrons from the chlorine. We give it to the, so that is actually a dative bond, so that the oxygen will have a total of 8 electrons. Remember, oxygen needs 2 electrons. So in this case, it's a single bond. Normally oxygen would make 2 bonds, but if it's a single bond, then that means it's a dative bond from the chlorine. Now the chlorine is in group 7. It already used 1, 2, 3, 4 of its electrons, so it is left with 3 electrons away from bonding. So they are non-bonding electrons. Now give the reason why chlorine dioxide is not a linear molecule. So if we have this kind of dot and cross diagram, that means the chlorine has non-bonding electrons, and the non-bonding electrons repel the bonding pairs of electrons, and that means it cannot be linear. It has to be just like water, for example, so it is non-linear. Chlorine dioxide can be made from potassium chlorate in a 2-step process. Potassium chlorate reacts with concentrated sulfuric acid to form a compound A, and then compound A undergoes a disproportionation reaction to form chlorine dioxide and hydrogen chlorate. State the meaning of the Roman numerals in chlorate V and VII. What does that stand for? These indicate the oxidation numbers of the chlorine. So when we say chlorate 5, that means that the oxidation number of chlorine is +5, and VII, of course, is 7. So this indicates that the chlorate has an oxidation number of +7. State the oxidation number of chlorine in chlorine dioxide. This was chlorine dioxide, and you should know that if we're trying to calculate oxidation number, each oxygen is -2. That means I have a total of -4, and that means the chlorine has to be +4 to have an overall charge of 0, since the ClO2 does not have a positive or a negative on it. In step 2, compound A undergoes disproportionation reaction. Deduce the possible range of oxidation numbers for the chlorine in compound A. Well, chlorine, we're told that compound A gives chlorine dioxide and hydrogen chlorate. Well, we said that the oxidation number of chlorine in chlorine dioxide is +4. Oxidation number of chlorine in the hydrogen chlorate, if we sit down and calculate it, we have 4 oxygens, so that's a total of -8. Hydrogen is +1, so chlorine must be +7. So in between +4 and +7, that is what we should have compound A, because we said disproportionation means that compound A will undergo oxidation and reduction in the same reaction. So the oxidation number of chlorine in A must be somewhere between +5 or +6, so that once it will be reduced going down to +4, and once it will be oxidized going up to +7. Compound A has Mr 84.5. A composition by mass of these percentages, and the remainder is oxygen. Deduce the molecular formula of A. Of course, if we're given percentages, then you need to get the empirical formula first. So we have the percentage of hydrogen, percentage of chlorine, and the rest of the 100 is the oxygen. How do we get empirical formula? Divide each one by its mass number, and the numbers that come out divide by the smallest. This gives me a ratio of 1 to 1 to 3. So this means that the empirical formula is HClO3. Now if I calculate the amount of that, it is already 84.5, and that means that is also the molecular formula of A. Write an equation for each of the two steps in the formation of chlorine dioxide using your answers in B. So what are the two steps? The first step said potassium chlorate reacts with concentrated sulfuric acid to form compound A. We already determined that A is HClO3. So potassium chlorate, this is the formula, plus sulfuric acid to give the compound A, which we already decided is HClO3, plus what? Plus the rest. So potassium chlorate plus sulfuric acid will give something plus potassium sulfate. Please take note of the formula of each one and do not leave the equation without balancing. So is this balanced or does it need balancing? You'll find that you will need to put 2 in front of the KClO3 and 2 in front of the HClO3 in order to balance the equation. Then we need an equation for step 2. Step 2 in which the compound A undergoes disproportionation to form chlorine dioxide and hydrogen chlorate. So the HClO3, which is compound A, we're already told that it will give chlorine dioxide, which we were given ClO2, plus HClO4. You will find that you will need to add H2O in order to balance all of this, and the balancing should be something like this. Remember to balance any equation that is written. One industrial preparation of ethanol is by the catalyzed hydration of ethene via a reversible reaction. So we have this reversible reaction, and we're told the hydration of ethene requires a catalyst which is coated onto a solid silicon dioxide support. Identify the catalyst. So this is hydration of ethene, in which we react the ethene with steam. What was the catalyst? You should know. Phosphoric acid catalyst. Under these conditions, the conversion of ethene to ethanol is only 5%, but the overall yield of ethanol is 95%. So just what happens to the equilibrium mixture containing ethanol so that we increase the yield to 95%? If we have this reversible reaction, how do we get as much ethanol as possible? Remember, as the ethanol is being formed, it is cooled and removed from the equilibrium mixture. So ethanol is cooled and liquefied, so it is removed from the equilibrium mixture, and then the reactants that have not been used are recycled over the catalyst. This is one of the methods in order to give as much yield as possible from a reversible reaction. Remove the product as it is being formed, and the remaining reactants are again recycled over the catalyst. The temperature used is 300 degrees Celsius and the pressure is 7 megapascal. These and the amount of water present in the reaction mixture are all compromises. Now explain why the temperature used is a compromise. So if I have this reversible reaction, and notice that the delta H for that reaction is a negative value, and that means the forward reaction here is exothermic. Now, why am I using 300? Compromise means why not more, why not less? So remember that we use 300 degrees Celsius because the forward reaction is exo. So I cannot use higher temperatures. A temperature that is too high would shift the equilibrium to the left and give lower yield of ethanol. But then I cannot go too low. So in order to go forward, I need to lower the temperature, but I cannot go too low because lower temperature would decrease the rate of the reaction. So usually if the forward is exo, I don't want it to be too high so that it doesn't go back to the endothermic side. And at the same time, I don't want it too low because that would affect the rate of the reaction. Explain why a manufacturer might suggest a pressure of greater than the compromise pressure. So why is it that I should use actually a higher pressure? Remember, according to this reaction, a higher pressure would cause the equilibrium to shift to which side? Remember, the higher pressure shifts to the side with less moles. So if I use a higher pressure here, it should shift the reaction to the right or go forward and give a higher yield of ethanol, since the forward reaction is the one that gives less moles. At pressures greater than 7 megapascal, a waxy solid forms which melts over a range of temperatures. Identify by name or formula this solid. Now, this was the reaction and we were working with ethene. But he's saying at very high pressure, it could form something else. You should remember that alkenes can form what? They can form polymers. So this double bond can be opened and joined to other monomers so that we get what we call polyethene. That is a polymer that would be a waxy solid. Give one other reason for not operating the process at a pressure greater than 7 megapascal. Remember, we said we cannot do reactions in general at very high pressure because that requires special equipment which is too expensive. Increasing the amount of water in the reaction mixture without changing the pressure might also be suggested. Remember, if I add more of the reactants, so adding more of the steam in the reaction would cause this equilibrium to go forward. Now, suggest one advantage and one disadvantage of increasing the amount of water. So as we said, increasing the amount of water will shift the equilibrium to the right. So that would give higher yield. But then that would mean that we have too much water condensing with the ethanol, and we will need to separate that mixture. We don't want the ethanol with water, we'll have to separate it. Okay, question 20 says, terpenes and terpenoids are groups of chemicals found in plants. They contribute to the smell and taste of the plant and so are used in flavorings and perfumes. Both terpenes and terpenoids have carbon skeletons based on one or more units of the compound isoprene. So we are going to be talking about this compound, which he calls isoprene. Terpenes are made up of two or more of these units joined together, while terpenoids have additional functional groups often containing oxygen. Limonene and myrcene are both terpenes composed of two isoprene units. Menthol, linalool, and citronellol are terpenoids containing an OH group. So the first question is, give the IUPAC name for this compound. So how am I going to name this compound? Remember, we look for the longest chain, so that is 4 carbons. and then my substituent, we start counting from the side that will give the lower number for the substituent. So this is actually 2-methyl buta 1,3-diene. We have two double bonds, that is called diene. One is on carbon number 1 and the other is on carbon number 3. The peaks with the highest intensity in the mass spectrum of isoprene are at m over z 68 and m over z 53. Identify the species responsible for these two peaks. So we're looking at isoprene, which is this. Now, what would give m over z 68? Well, actually, the total MR of the compound is 68, so that structure, all of it is 68. Remember, you must have a positive sign for the fragments. What about m over z 53? Which part of this molecule would give me an MR of 53? Well, if we just ignore the methyl group on the left, all the rest is C4H5, so that is an MR of 53, so it is all this part with a positive charge. The infrared spectrum of isoprene is shown. State the origins of the peaks labeled P, Q, and R. You may use a label diagram. Use the data booklet as a source of information. Of course, this is the isoprene, so we go to the data booklet and we look how does this compound give these peaks. You will find from the data booklet that there is a peak for the CH part at 2962, so that would be the Q. Q is CH of the alkane, and we have a CH of alkene at 3095, for example, so that other peak on the left is for the CH of an alkene. What is R? R is for the C double bond C of an alkene. You get all of these from the data booklet and translated into the spectrum. Show that myrcene, limonene are terpenes by comparing the molecular and or empirical formulas of all of these. Remember, we were told in the introduction that terpenes are made up of 2 or more isoprene units joined together. So if we look at the molecular formula of each of these, first of all, the isoprene, we already said the MR is 68. Now, if we look at the others, the MR, the molecular formula of each of these is C10H16, and that is actually twice that of isoprene, and that means that each of them is made up of 2 units of isoprene. Both myrcene and limonene can be completely hydrogenated by reaction with hydrogen. First of all, state the conditions required for hydrogenation of alkenes. Remember, if I have an alkene, I want to react it with hydrogen. First of all, that means the double bond opens up and we add H and H, so we're changing the alkene to alkane. Now, what are the conditions? We have hydrogen with nickel catalyst and heat. So our condition is nickel catalyst and heat. 5-gram samples of myrcene and limonene were completely hydrogenated. Calculate the volume of hydrogen needed for each sample. So we already know that these are the structures of myrcene and limonene, and that means the myrcene has 3 double bonds while the limonene has 2, and you should realize that each double bond needs 1 mole of hydrogen. So if we're starting with 5-gram samples of myrcene and we said each of them has a formula of C10H16, I can get the MR. The MR for each of them is 136. use that to get the number of moles for each of them. We have 5 grams of each, so 5 over the MR, mass over molecular mass. This is the number of moles for each of them. Now, you should realize we said for myrcene has 3 double bonds. That means if this is the number of moles of the myrcene, the number of moles of hydrogen will be 3 times of that. And then I can get the volume of hydrogen. The volume is the number of moles times 24. We multiply by 1,000 because we are required to get it in centimeter cubed. What about limonene? The same, but the limonene has 2 double bonds, so it will need twice the number of moles. So the number of moles of hydrogen will be twice the number of moles of the compound, and the volume is the number of moles times 24,000 to give the volume in centimeter cubed. Give the IUPAC name of the product formed by complete hydrogenation of myrcene. First of all, this was myrcene, and we said it needs 3 hydrogens, so all the double bonds are now single bonds. What is the name of that product? Again, to name the product, we choose the longest chain. So we have a chain that has 8 carbons. You should remember that 8 is oct, so this is an octane, and we start numbering from the side that gives the lower number for the substituents. So this is 2,6-dimethyl, to indicate that I have 2 of them, on octane. So 2,6-dimethyl octane. 3 students were asked to carry out a single chemical test to unambiguously identify the presence of the OH group in the 3 compounds. So I need a test for OH that can work with all 3. Which test? So the first student tried using acidified potassium dichromate to oxidize the alcohols. The second tried acidified potassium manganate, an oxidizing agent similar to the potassium dichromate. The third student tried using phosphorus pentachloride, criticized the 3 students' suggestions by linking the expected results and the actual observations that would be made for each test and the structures of the 3 alcohols. Now, what is the difference between the 3 alcohols? Well, menthol, you should realize, is what type of alcohol? It's a secondary. Linalol is a tertiary, and citronellol is a primary alcohol. So, which of these tests will work with all 3? You should realize that to test for alcohols, the one that works with all types of alcohols is phosphorus pentachloride. So PCl5 would be the best reagent since it reacts with all the 3 alcohols to give misty white fumes, and this test is used to identify presence of alcohols. What about the others? Potassium dichromate. Would potassium dichromate react with all of them? Well, remember that potassium dichromate, which is originally orange and turns to green because we are required to give the observations, it will do that only with a primary or a secondary. It will not react with the tertiary alcohol, so linalol will give no change. Remember, the secondary alcohol, menthol, is oxidized to ketone, while the primary alcohol, which is the citronellol, it would eventually give carboxylic acid. But the tertiary alcohol will not react, so this cannot be used as a test for the presence of an alcohol group in general. Well, what about potassium manganate? The problem with potassium manganate is that it reacts with both the alcohol part and with the alkene part. Remember that alkenes react with potassium manganate to give diols. So the potassium manganate is not used as a test for presence of alcohols because it not only identifies the presence of alcohol, it could also be used to identify the double bond, so that cannot be used to identify alcohols. And that's the end of the paper. I hope this was useful to you, and good luck on your exam.